Hello and welcome to part 7 of our lithium batteries lecture. In this video we'll talk about the service life, self-discharge and safety aspects of lithium batteries. Lithium-ion cell service life and aging are typically determined in relation to the service life over time or to the numbers of cycles we can take out of a lithium battery. Changes in the cell's conditions are measured in terms of the cell's capacity loss. The relevant external factors are aging over time is temperature and the state of charge, and the cycle life depends on charging and discharging rate, temperature, state of charge, depth of discharge. The external factors are also called the stress factors for batteries. Here again, we only have a look to the lithium, nickel, manganese, cobalt system. The cell capacity to number of cycles for various depths of discharge, and all the discharge currents we see here is 1C. A cell's end of life is typically defined when the usable capacity of the cell falls to 80% of its initial capacity. With other active material systems, the relationships and the resulting service lives differ, so that is not for all lithium batteries we see here. Lithium-ion cells typically have a very low self-discharge rate. Capacity loss per year and not per month at room temperature is in the range of less than 3% with an average state of charge. But at high temperatures it also can rise of up to 15%. Since self-discharge generally increases as storage temperature and state of charge increases, cell storage temperature and state of charge are the key factors for these cells. If lithium-ion cells are stored over long periods while monitored by electronics powered by the cells themselves, then the electricity consumption of the monitoring electronics must also be taken into account together with the cell's own self-discharge. At the electrode level, loss of contact between the active material particles is one of the aging factors. The contacts are broken due to mechanical stress caused by volume change during lithium-ion intercalation and deintercalation. This results in a loss of electrochemically active material as well as an increase in internal resistance. Another factor is the continued growth of the SEI layer, increasing the internal resistance of the cell. If fissures develop within the SEI intermediate layer, when the SEI layer is formed again, lithium is gradually consumed and the concentration of charge carriers is reduced. A final factor of the successive separation of the transition metal ions, the layered oxides, by the electrolyte. The thermal decomposition of the positive electrode materials is frequently a focus with the safety of lithium-ion cells. Studies on this subject demonstrate that depending on the material, decomposition occurs at temperatures ranging from 150 degrees Celsius to 250 degrees Celsius. Thermally initiated decomposition releases that then further accelerates the decomposition of the active material. This is termed as the thermal runaway. If oxygen released during decomposition, as with transition metal oxides currently under consideration, an enormous amount of heat may be produced. That is unlike with the lithium ferrum phosphate, for example, which does not release oxygen. Other factors, such as the thermal stability of the negative electrode, the electrolyte, or other cell components must also be taken into account. In addition, boundary conditions determined by cell design and potential manufacturing or assembly errors also play a role. The separators are designed to remain stable up to temperatures of about 130 to 150 degrees Celsius. The upper temperature limit for the use of an electrolyte is determined primarily by the thermal stability. of the conducting salts found in the solution and by the side reactions. The most commonly used conducting salts begin to decompose at temperatures of around 100 degrees Celsius. Since chemical reactions accelerate at high temperatures, Arrhenius equation, higher cell temperatures increase all the reactions. This in turn increases SEI layer formation, increased internal resistance. It also can result in gas formation and cell bulking. In addition, at temperatures bigger than 70 degrees Celsius, the SEI passivation layer decomposes more rapidly. Since these reactions are generally exothermal, heat is released and the cell temperature rises. If a lithium-ion cell is thermally well insulated, the heat released may trigger the thermal runaway. At lower temperatures, around -30 degrees to -20 degrees, the separation of solvent components by freezing is usually reversible, but the SEI decomposition reactions and other side reactions at higher temperature are irreversible. As a result, the permitted operational temperature range of EC-based electrolytes typically ranges from -20 to around +50–60 degrees Celsius. If abnormal operating conditions lead to the cell being opened, highly flammable components such as DMC, DEC and EMC may pose a serious risk. New electrolytes are increasingly mixed with additives that hinder the decomposition reactions and reduce, therefore, flammability. Ending here with a small outlook on lithium battery systems. Lithium-ion cells remain a focus of current research and development. Although a lithium-ion cell service life of several hundred cells and several years, less than 5 years, is acceptable for consumer applications, they are absolutely inadequate for many industrial applications. These applications require higher current capacity and faster charging capacity, as well as improved energy density, service life and safety. For example, fast charging batteries are required for storing brake energy with recuperation in hybrid cars. Service lives of bigger than 10 years are required for storages in electricity networks. Engineering lithium-ion technology for these purposes will require significant scientific and technical advances. Improving the high current capacity of large format lithium cells will also require a better understanding of the relationship between material synthesis, electrode design, particle size, morphology, distribution, porosity, composition and performance characteristic, current rates, internal resistances. To increase energy density, new positive and negative electrode active materials are currently under development. Examples include transition metal phosphates. So they have high voltage olivine around 5 volts, such as the lithium manganese phosphate, the lithium cobalt phosphate or the lithium nickel phosphate. Hyperstoichiometric layers oxides, new manganese spinels and mixtures of various active materials. Use of these new compounds also requires new electrolytes that can cover a range of redox potentials in this electrochemical voltage window. Due to their high specific capacities, silicon and tin alloys, as well as silicon-carbon composite materials, may be appropriate for the negative electrode. Since lithium intercalation and deintercalation result in enormous volume expansion, use of these materials also requires effectively compensating for mechanical stress. Currently, electrolyte additives are a focus of research. What are termed shuttle mechanisms may be used to improve safety. After a certain cell voltage is reached, the voltage of the cell is prevented from increasing further by the onset of a reversible reaction to the additive. Alternatively, when a certain voltage is reached, the onset of additive polymerization increases the internal resistance. This in turn causes cell shutdowns. Polymer or other solid electrolytes could be considered as a replacement for liquid electrolytes as well. This would eliminate the risk of electrolyte leakage and possibly avoid the need for a classical separator. Due to their high internal resistance, their use so far has been limited. Alternatives are currently under study. And the last video we will show soon, that will summarize what we have shown in these first 7 videos. But before going to the video with having more photos, video sections in it, we ask a few questions to control what we have learned. And that is, first, what is meant by the term intercalation? What determines the cell voltage of a lithium battery cell? What are typical figures for the practically usable specific capacity of the positive active materials? And what are typical cell voltages? Which 3 types of electrolytes can be used in lithium battery cells? What is the role of lithium phosphor fluoride? Which materials are used as a separator? Of which material collectors are made of? Which factors must be taken into account when considering lithium-ion cell behavior and internal resistance? What makes the difference between the high performance or high energy cells? Which parameters should be monitored carefully? To ensure a long service life, in which range the state of charge of a lithium-ion cell should ideally be? What is a thermal runaway? So thank you very much for your attention.